Okay, so welcome back. So our third speaker is Professor Mohammad Hajiaghayi from Maryland, the University of Maryland. Professor Hajiaghayi received his PhD from MIT. He did postdocs at MIT and CMU. So before joining the University of Maryland, he was a senior researcher in the in the algorithms and theoretical computer science group at AT&T Labs. So today he will talk about classical problems with modern techniques. So let's welcome.
Okay, thanks for the introduction, and thanks for the audience who came to the talk, and thanks for the organizers. It's a great conference that you have here. Good. So before starting with the talk, which is about price collecting framework, in which I'm talking about some classic problem with some modern techniques, I want to say this is like a movement that I try to essentially propagate, that I ask all people, essentially professors, to put their courses online, especially nowadays after COVID. It's very easy to record it and put it online. And this is essentially that science for humanity. You can put it such that everyone is using it. I'm putting all my courses online. It is my YouTube, and you can go and watch them. There are playlists for each of them, and I really encourage everyone is putting it there, because then they are very useful, especially for graduate students or undergrads. They can go and watch them anytime, and they don't need to take the class anymore. Anyhow, that's about the YouTube things, and these are my other social media things. If you want, you can follow me, and there are news are there. You can see it there. Great. Now let's go to price collecting problem. What are price collecting problems? So price collecting problems are classic optimization problems. Generally, what is the goal in this problem is that there are some optimization problem, you need to satisfy some demands, some variables that you need to some variables demand that you need to satisfy them. And you want to get a low cost structure for that. Now, what about now? This is the classic optimization. What about the price collecting framework? There is that, okay, these are some of the demands. You may decide that you don't want to serve them and just pay the penalty. That's the concept of essentially price collecting frameworks. And why do we call them actually price collecting? It seems more penalty. The original objective function actually for these price collecting problems, the people consider like here, what are the objective function here? You try to minimize the cost, essentially that for those that you are serving or satisfying, plus penalties of those that you are refused to satisfy them. In the original version, I mean the one that maybe originally defined, they consider the cost minus price. What's the meaning of that? It means that, okay, you are paying some cost, and for any cost that you pay, you will satisfy some of them, you will get some price back. So the objective was essentially cost minus price, price essentially, because these prices are the money that you were collecting and the cost the one that you were paying. What is the problem? The problem is that this, if you consider cost minus price, generally when you have minus in the objective function, it can, the objective function can be very small, and it is very hard to follow it or essentially trace it, and essentially becomes inapproximable. That's the reason that they consider this version, that is now it has only additions. You will consider the cost of essentially a structure that you have it plus the penalties. That's the reason that is called essentially, for historical reason, called still price collecting problems, but really it is cost plus penalty. It has lots of application in theory and practice. So one important thing, actually this price collecting problem, you all know nowadays for MLS stuff, these are just Lagrangian relaxation of the regular problems. Generally, if you consider, for example, these problems that, like for example, KMST, you want to connect at least k nodes in a graph, or other function, generally when you consider the Lagrangian relaxation, becomes the price collecting problem. So these are actually very general set of problems. Other than that, these are actually a host of new algorithms and techniques. I will mention some of them. For example, we are introducing a clustering algorithm for this that has applications in ML and approximating other problems, etc. Other than ML applications, also these are some of the things that actually this problem had real-world applications. I was like the time that I was at AT&T for like telecommunication network. What was the problem here? Say that you want to design a fiber that connect essentially customer to the existing network. You have a graph. You can consider a street network for metro area. And the root is the existing fiber. So you want to essentially connect new customers. But what is the edge cost? The edge cost is that you need to dig trench, put fibers and other stuff, and that's very expensive. This thing essentially is super expensive, especially like in the US, it's even more expensive. And here, when you do that, you will connect some of these people, then you get the price. The price in this case would be this monthly money that you will get it. You can think about for a year, how much I will get it for connecting this customer. Now, think about that a person is on top of the mountain. And you may not want to satisfy that. You may ask essentially, I don't know, from Starlink or others that they can put some satellite connection for that person and just pay the penalty for that. And this is because of the governmental reasons. You need to still satisfy that guy somehow. That's the reason that you need to pay the penalty to another third party such as satisfied. So that's the applications. So in this talk, I want to go more through this. This is the framework that I have mentioned. You can consider it essentially for lots of applications. So it's very general. Here I want to talk more about some fundamental network design problems and say essentially the applications for those problems. But again, you can consider it in a very general settings. There is no need to just consider this stuff. Okay, so let's go to this very fundamental network design problem. The first one that everyone knows is essentially MST, minimum spanning tree. You want to connect all the nodes in a graph. This is the very basic thing in any introduction to algorithm. You need to know about Kruskal algorithms, Prim. Another one maybe you heard less, Brovka. That's another one actually, but these are like very famous ones. Now let's go one level more in terms of generalization. Steiner Tree and TSP. So in this problem, these are generalization of MST. A weighted graph is given to you and set of vertices called terminals. Here the idea is that, okay, I don't want to connect everyone. I just want to connect a subset of them. Now this connection can be essentially just as a tree you want to connect them, or you want to connect them as a tour, which would be TSP. These are actually very fundamental problems again. This Steiner Tree actually goes, I think, the introduction to Gauss in 1836 that introduced this problem. And for TSP, this is 1832. There was in some articles, books, etc. I didn't find who introduced it actually, but it's like a very famous problem. And let me just give you an example here. I mean, this is the problem. Say, for example, these are these three nodes that you want to connect. Not all of them. This guy, I mean, you don't care. And you want to connect them. So if you want to just connect among them, if this node is not there, then the cost would be 2 plus 2, which would be 4. However, if this guy is there, this is called the Steiner point. Then you can only pay a factor 3. Like essentially the cost would be 3. And you can generalize this one. Currently you get the ratio of 4/3, but it can be essentially instead of a cycle of length 3, you can consider a cycle of length n, and this ratio actually approaches to 2. So this is essentially for these problems. You can essentially do the same thing for TSP, and then TSP actually is important. Interesting thing, lots of algorithms are based on, for example, MST or Steiner Tree. I will focus more on Steiner Tree because I'm talking about two tree generalization of that. But generally, the techniques for here also can be applied for this, or for several problems, not maybe for everything. The best approximation for a minimum spanning tree is 1.39. This was in, I think it's like 2010. But there were lots of papers that I'm talking about. I don't mention the conferences or journals. These are just top soda fox stock or JCM SciComp papers. And here, the best for TSP is 1.5 minus epsilon for some constant epsilon. The people worked a lot essentially. And both of these actually got the best paper award in top conferences. So these are like super important problems. Now, let's go to the next problem, Steiner Forest. What is a Steiner Forest? Here, a set of pairs of vertices called demands. And you just want to connect these demands. You don't care about everything. So let's see an example. So this is an example. Here, consider these two nodes should be connected, these two orange guys, and these two green guys. You can connect these guys, essentially 1 plus 1 would be 2. And this green guy, you can connect 2. But you don't need to connect everything here. This 20 and 30 here, there is no need to connect everything. Of course, if you connect everything, then your demands have been essentially satisfied as well. But there is no need to do that. And optimum may not do that. In this case, the optimum would be essentially 2 plus 2, which is 4. So if you want to connect all of them, probably I need to at least pay 20. The best approximation for this one is 2 approximation. And believe it or not, this is the problem that remains actually probably one of the biggest problem in optimization in terms, especially for theoretical reasons, getting something better than 2. We don't know whether anything better than 2 is possible or not for this problem. And indeed, this was the part of this. This 2 can be generalized for a Steiner network. This is the great work of Agrawal, Klein, Ravi, 91. I think the original work was actually 89, so 35 years ago. They consider generalization of a Steiner Forest. Here, the goal is that you not only you want to, so between these two guys, not only like you want to connect them, but you want to higher connectivity. You may want to have, instead of one essentially path, you may want to have 2, 3, or in general, Ri disjoint paths. For this problem, even this generalization, we can get to approximation. But of course, the improvement, there is no improvement because first you need to improve this big problem. And we don't know whether it is any, there is no hardness for that. For a Steiner tree, this was what, as I mentioned, the best paper award in stock in, I think, 2010. There are a series of work, essentially, maybe, I don't know, 8, 9 work that everyone essentially improving below 2. But nothing for Steiner Forest. Good. Now, let me just say this problem, the price collecting version of this problem. So, price collecting a Steiner tree. What's the meaning of that? It means that you are given a set of terminals. You want to connect some of them, pay the cost of these guys, and then for the rest, you want to pay the penalty. What are the best things? So, this is actually classic problems. This is the Venestech 93. This actually, the problem, the price collecting was introduced by Ballas in 89. And this, I think the conference version appeared actually sooner. There was 3 approximation. Then there was this result, Gomans and Williamson, 92, 2 approximation primal dual algorithm. They actually consider a Steiner tree, a Steiner Forest. This is, and they give a 2 approximation, a clean one that Agrawal, Klein, Ravi also gave, but this is a cleaner primal dual algorithms. They also give 2 approximation for this price collecting Steiner tree. The big open problem actually that Gomans put it in a slide in some presentations and in some slides was, can we get below 2? Always getting like below 2 was the important thing. That happened in this paper that we had it in 2009, and we could actually break this barrier of 2 to get it 1.967. Very recently in this stock 2024, we could get actually substantially below 2, 1.79. And I will talk about these results. Next one, TSP. For TSP, again, the same problem. You are a set of nodes. Now you want to connect them as a tool. For the rest, you want to say, pay the penalty. What is the state of the art for this one? Again, this one is introduced in particular, Ballas 89. There was 3 approximation. and this was again the conference version, I think was sooner. Then this was two approximation, primal, dual by Gomez and Williamson, and that comes from Steiner Tree as well. So essentially, price collecting Steiner Tree played very important role. Once you had that one, then this was not hard to get it. And then again, Gomez mentioned, can we improve this one also below 2? And that's the thing that we have done it in 2009. We could get 1.9. There are some now more works here. There was, after us, Gomez could improve it to 1.91. This was a stock last year that they could get 1.74. And this is an IPCO this year that they could get 1.59. Go back to the next one, price collecting Steiner Forest. Again, the same problem. You want to connect, essentially here you want to select a subset of edges in this graph. So here, those nodes with the same color are the demands. So here, these are the demands. So you are essentially you are selecting or buying a set of edges here. For them, you are paying their cost. So we are buying this essentially here, these blue edges. But there are two demands that we don't satisfy, these guys and these guys. And we want to minimize the sum. This actually, this version of, as I mentioned, the Steiner Forest, I mean, they call it generalized the Steiner Tree. It was considered by Gomez and Williamson in '92. They gave two approximations for non-price collecting version. For price collecting Steiner Tree, they gave two approximations as well as price collecting TSP. But essentially, they leave the problem open. What about for price collecting Steiner Forest? Can we get two? This was actually a big open problem. Even getting constant was not a trivial one. Until this was this work that we had it with Kamal Jen in 2006, that we could get three approximation, and then using some technique. This technique is actually, the technique is attributed to Michel Gomez. You could improve that one to 2.54. So what was the big open problem here is that can we get a two approximation also for this problem? The people actually work quite a bit on that, like even before or after our work especially. And it was a hard problem because I worked on it also for a while and couldn't solve it actually. And more interestingly, in 2017, there was this result that gives 2.25 integrality gap for that. He said that the natural LP that the people are writing it actually has a gap higher than 2. You cannot get 2. So this was actually a big problem that, I mean, I spent a lot of time, I couldn't do that. But I mean, thanks to my smart students actually, we could finally get these results essentially done, and you get a true approximation. And this is by a very natural algorithm that actually maybe the people have considered this algorithm, but they couldn't analyze it. We analyze it, I mean, like nicely, and then it is also built on this work, but this recursive things is a nice one. I'm talking about this algorithm as well. This talk. So yeah, so this was actually breakthrough that several people worked on it, especially given this integrality gap that they say that you cannot. And integrality gap for the LP generally is like, it means that this LP, at least in the usual way, you cannot get something better than this approximation unless you do something non-trivial. Okay, now let's go to price collecting Steiner network. So in the price collecting Steiner network, what is that? This is the graph is given to you. And then we are given a decreasing penalty function. So what is this penalty function? It said that, okay, between these two pairs, you should essentially connect them. Now, if you just connect them, maybe you will pay a certain penalty. But if you connect it via two different paths, generally, essentially, these two different paths is for reliability in network. You want more essentially paths. You want higher connectivity. If something happens, at least there is another path. Then you pay less penalty. And if you connected 3, then you pay less penalty. But after 4, if you connect it like 4 different paths, then you pay 0 or 5 or anything else. So the objective here is that the set of edges that you will buy, and then based on the connectivity of this guy, this is the connectivity requirement. This is the penalty function that says that if the between SI and TI, this is the connectivity, how much you should pay. So this problem actually is equivalent of the all or nothing version. So what is it? So here, as I mentioned, for different connectivity, you pay different things, and it is decreasing. It means that if you connect more, then you pay less. This all or nothing is this one. It just says that if you are connected by Ri, then you don't pay any penalty. If it is connected by less than Ri, then you need to pay the whole penalty. So there is no this kind of a step function. Of course, this is a special case of this, but it is equivalent of this. These two problems are equivalent. So for this, also we give 2.54 in this 2010 paper. I just want to give you, so I try to essentially give some ideas about general set of price collecting problems for network design. Again, you can define it for other problems, but these are very fundamental problems, and I want to give you some ideas that what we can do essentially. So this was the set of problems that we are considering here. And again, from more special cases to more general cases. Now I'm giving some ideas about in the rest of the talk, about the more general case, and then go to the specialized case, and then we discuss that, how we can improve them. So it's somehow the reverse of this that we discussed. But before that, I wanted to give some ideas of why these problems are important, especially in optimization. So when we talk about non-price collecting version, we essentially mean the regular problem that you need to satisfy all demands. Now, the main question is that, is there a distinction between price collecting versions of the problem and the regular problem for different problems like TSB and others? I mentioned there are some of these problems. For some, like for example, Steiner Forest, we have the matching bound, but for others, we don't have the matching bound. So there is one instance that there is some separation. So this is a Steiner Forest problem on planar graphs, the graph that you can be drawn on a plane such that no edges essentially no edges intersect. For this one, there is a p-task means 1 plus epsilon approximation for a Steiner Forest, but for price collecting a Steiner Forest, it is apx hard on this graph. Apx hard means that there is no 1 plus epsilon approximation. That was, I think, the JCM paper that we had it with Marks and Botany. However, for others, we don't have any separation. So far, we don't know whether price collecting problems are really harder than regular problems, or maybe you can say plus epsilon, you can always solve it. We don't know that. And this one I mentioned, is it really a separation? There is also some discussion here whether this is the case or not. A little bit of cheating is there, because when we talk about the Steiner Forest on planar graphs, the whole thing is planar. But we have some kind of demand graph, and this demand graph may be not planar. That's the reason that it is not quite a separation, because maybe not that satisfactory separation between these problems. Because essentially you have another demand graph which is not planar, and so, but anyhow, that's the thing that we know for now. For other problems, we don't know anything, essentially. We don't know whether there is a gap or there is a hardness or anything here. But what we know is that we know. There is a constant factor, and indeed an additive factor 1 difference for approximation factor of price collecting versions and non-price collecting versions. But even this is not trivial things. I want to give you an example, and then we will go from there. So generally, you can get +1. I will say what is the technique to get +1. But even this +1 is not a trivial one. But again, the main question is that, is it +1 or some constant or epsilon? For any epsilon, we can be that close essentially. So let me tell you first this problem to reduction to all or nothing problem for this version. I just give you the general idea. So again, coming back to this problem, so we had this penalty function which was decreasing. Now, in the all or nothing, you don't have these steps. You have only one threshold. Either you satisfy it or do not satisfy it. And the way to do it, that is actually not that hard, essentially. If you have this penalty function, you can consider this one. You essentially create these things. And then instead of one pair here, you will put several pairs. Instead of one pair here, you will put essentially 3 pairs here. And then these three pairs would be all or nothing. So and essentially, in some sense, you will put all of them together. Now, the first pair says that if you satisfy me by essentially up to 2, then you should not pay any penalty, otherwise you should pay the penalty. The second pair says that, okay, if this is like, I don't know, 8, if you satisfy me essentially up to 8, then you don't need to pay any penalty, otherwise you should pay the penalty. And so on and so forth. So essentially, this all or general version can be essentially solved by all or nothing version. But even the all or nothing, as I mentioned, is non-trivial. So again, we are talking about the general case. In the all or nothing, this is not a trivial case. So let's write an LP. This is the way essentially you can write an LP. This is a general problem. So this, what is this? You try to minimize the cost of the edges that you buy plus pay the penalties. This ZI essentially says that whether you have satisfied or not. ZI equal to 1 means that you have essentially not satisfied this guy. And ZI equal to 0 in the integer case means that you have satisfied this guy. As you can see, this is like, it is essentially this Lagrangian relaxation. Now, you will write this LP essentially for the problem. So this is a regular thing that you will write it for. Yeah. So if there was no penalty here, that was the thing. If you want to solve essentially the LP for this problem, the IP and essentially the corresponding LP, you say that for any cut, I need to, if you want to have essentially R disjoint path from S to T, if you consider any cut that contains S and not T, you should have at least R edges that you bound there. That's essentially the one that you are putting it here. But now this is the price collecting, this is the essentially price collecting version. You will say, this is the natural one, it says that it should be greater than 1 minus Vi times Ri. What's the meaning of that? It means that if you paid the penalty 1, then there is no requirement. You don't need to connect this guy. You are free to do whatever. But if, in the integer case, but if Vi is equal to 0, it means that you don't want to pay the penalty, then you need to buy essentially this one. This is a natural problem essentially for this. And just see how you can get this +1, just idea. So the +1 idea comes from this. If all, for Steiner Forest, for Steiner Forest, all the requirements are just connecting to a path. So Ri would be equal to 1. In that case, the problem would be easy. How you can get essentially +1. So you will consider all Ri's, and this is the Steiner Forest essentially. Consider all pairs that the ZI is greater than 1 over 3. It means that you are paying at least 1/3 of the penalty. What do we do? So, okay, I'm paying the full penalty for these guys. How much do I incur? A factor 3, because I'm just multiplying everything by 3. Now, for those guys that you didn't pay, this means that ZI is less than 1/3. It means that you have at least satisfied 2/3 of the connectivity. Then you will multiply all this XE essentially by a factor 3 over 2. And then this becomes essentially the regular non-price collecting version that the integrality gap for that would be 2. Integrality gap, it means that if there is an LP, then you can actually round it to an integer solution by paying a factor 2. So I'm paying a factor 3 over 2 here by multiplying everything by 3 over 2 times 2 would be 3. So the penalty would be 3 times this, and then the cost would be 3 times that. So you can get 3 approximation. So, as I mentioned, the non-price collecting version was only 2. So this is the general thing, but this does not work for this higher connectivity. Why? This is a bad example. Consider Ri equal to 4. So consider these two nodes. I want to have essentially 4 edge disjoint paths here. Now, if you can actually, LP can cheat. So there is no 4 disjoint paths. It means that you need to pay the penalty here. I mean, there is no way that you can connect it to these two to 4 disjoint paths. However, LP, essentially can cheat, and we put Vi is equal to 1 over 4. Then it satisfies this, and then essentially it pays the penalty Pi over 4. And say these costs are almost 0. So we know that the LP actually, the IP, the integer solution, should pay Pi because there is no way that you can connect it by 3. So IP has to put that. So there is a gap of essentially this. And so this LP does not work. So this +1 that I have mentioned is not working anymore here. This was actually an open problem of this paper that was in SODA 2008. And this is the trick that actually we used, and we could solve this one. You can, this is a nice trick that we could put it. You cannot put it on XE, but you need to add, essentially write some flow LP. And in the flow LP, you need to say that the flow on edge I, the flow of pair I on edge E can be at most 1 minus Vi. This is a trick that you can do it, and then here instead of XE, you are writing essentially this flow 6. If you do that, then you can see that in this example, LP cannot put Zi greater than 0 because it cannot satisfy this. So actually then LP also needs to put the, has to put the Zi actually equal to 1. I think this should be 1. Here. Like 1 minus Vi should be 0. So it needs to pay the penalty. And by this trick, actually we can get 2.54 for the general. First we can get 3, and then we can use that command technique to get it, these things. So this was solving that open problem. And also there are other generalizations. There are some other generalization. It is called this kind of submodular version, that you have a set of pairs, and the penalty that you are doing is a submodular function. According to who are the pairs that you have connected, you may pay a different penalty. Because somehow this says the correlation version. So I want to say that if certain pairs are connected, then maybe I don't want to pay that much penalty. But if just some arbitrary pair you connected, you need to pay higher penalties. Anyhow, this one also we could generalize it, and we could get this 2.54. So this is the most general version that I talk about it. Now, after talking about this, I want to go, and the rest of the talk I will focus on two important problems, especially price collecting Steiner Forest and price collecting Steiner Tree. So, as I mentioned, for price collecting problem, there are actually nice techniques that exist. And one of them is this price collecting clustering. This is price collecting clustering is the first work that we could actually introduce such that we could get below 2, that essential open problem of Gomez, that can we get below 2 for TSP, price collecting TSP, or price collecting Steiner Tree. So this found several applications, even in non-price collecting versions, even essentially in some ML algorithms. So what is this one essentially? Consider you want to cluster the vertices of a graph, and each vertex has a budget. You can consider each vertex, maybe you can consider this, you can consider the examples that you want to train essentially, I don't know, a neural net or anything. And the weight or the budget of each vertex is the number of instances that are essentially in your example. Then on top of that, between two different instances, you have some metric, which is essentially saying how much is the distance or how much is similarity. What we want to do, you want to somehow cluster these examples into a nice way of clustering. And for clustering, there are lots of objective functions. Some of these things actually we don't know even. This is one of these problems, it is unsupervised learning. So in some sense, we don't know what is the best clustering. In some cases, actually it works well, and this actually works in some cases quite well. So what do we want to do here? We want to essentially, so a cluster here, a tree that connects these vertices. So in some sense, these different examples that we have, we want to connect some of them, say, oh, these are in the same category, these are in the same category, etc. What is the connection cost of a cluster? So we want to have this one. The connection cost of a cluster is payable by the budget of its vertices. It means that you should have enough budget or enough essentially instances of these examples that somehow overcome the connection cost of these guys. So that means that you are in one cluster. But what about if you are not in one cluster? What's the meaning of that? It means that if you are in a different cluster, if I want to connect you, then the cost, the connection cost that I should pay, it should be more than your budget. So it's actually very natural things. So this is a more formal version of that again. So this is, for example, a network that you have it, you get this kind of clustering, regular clustering, and you want to say that the cost of these guys are payable by the budget of these guys. Somehow, essentially, you have enough credit to pay and somehow pay this distance in some sense. But this is the important one. If you consider like nodes from different trees, for example, this guy, this guy, this guy, this guy, this guy, then the connection cost of these guys would be more than their budget. So in some senses that these guys are far from each other. It's not a smart way to bring these guys together. That's essentially the intuition. And let me just give you, this is the one that I want to talk about it. This is called essentially this kind of clustering procedure. It comes from this, in some sense, from this primal dual algorithm that was by AKR, Gomez-Williamson, but doing it actually more combinatorially and more nice way. This is the way that we mentioned the coloring algorithm. And this coloring is important because if you are considering LP, like the type of thing that you can do is more limited. But this coloring actually gives you the power that you can solve this problem more algorithmically because you can do whatever you want to do as long as you know what's the meaning of these colors and you can prove the theorem. So in terms of flexibility to design algorithms are much greater thing. And that's the one that we have actually introduced in this 2009 paper essentially. So what is this coloring scheme? So you are essentially starting, so here you can think about this one that in this case, each of these nodes, they have their own color. And these are, again, you are given some graph, some nodes essentially that you have it. Each of them have some budget. And this budget essentially is the potential to grow this ball. So they are growing, and then when they grow, essentially, when one edge becomes tight, they are buying the edges in some kind of PFS manner. Then these edges becomes tight, then you will buy this, and then they can continue. When you continue, now, if you want to go there, one of these guys should pay for it. So that's the thing that they may alternately essentially pay for that, and the way that they should pay actually becomes important later for other problems. So you will do that, and then at the end, when they don't have enough budget, they run out of budget, then they stop. And these are the clusters that you obtain essentially. This is the cluster, this is the cluster, and this is the cluster. And these are two different clusters. So this is the way that you can do it, and then you can prove this property that I have mentioned. I mean, it's a bit more technical, but this is somehow, the main idea is this one, that if somebody wants to connect these guys from different clusters, they need to pay at least the radius of this ball. That's a very, essentially, intuitive thing that we are using this one a lot later. So if you want to, this is the color. If you want to go out of this color, at least you need to pay the total, essentially, the radius of this particular color. And you can say, for example, if you do that, if you now have such a tree, then the total cost of this tree would be greater than the budget of these guys. So you can, as I mentioned, this has been introduced in this paper with Aaron Archer, Hossein Bateni, and Howard Karloff in 2009. It was, I think, Fox 2009. Using that, we could get for price collecting a Steiner Tree and price collecting TSP, we could go below 2. But then we could use it essentially for planar Steiner Forest. It is not anything about price collecting here. Regular problem, you could use it, or you could use it for other problems. For example, planar multi-way, again, different things. It found several applications, these things, because it's a very natural clustering algorithm. And in some sense, it gives you some ideas what should be the shape of the optimum. You can go more about it. I just want to mention what is this and what are the applications. Now I'm going back essentially to the things I mentioned, the general things and the techniques. I want to go back now to talk about this two approximation Steiner Forest problem. That this was actually breakthrough things, and I want to talk about these results and the way that we are doing that. To give some ideas about this problem. After that, I will talk about two approximations. I'm talking about 1.79 for Steiner Tree. But this is the main one. This is the main work actually. The other work appeared in stock. It happens rarely that the consequence of this paper, actually, so the paper appears in the stock, but that's the case because the result here was important and we just wanted to send it to the first conference. That's the reason that we submitted to SODA. So, again, so that coloring scheme that I have mentioned, I want to repeat and then build on it. So, what is the problem here? So, here, this is essentially the coloring scheme that we consider for Steiner Forest. So, these are these guys that, first I'm talking about Steiner Forest and then generalize it for price collecting version. So, in the Steiner Forest, these are these two things that you want to connect and these two you want to connect. Each edge you can consider as a curve and the length of it is equal to weight of this. At any time we maintain a forest which is empty at the beginning, so we don't buy any edges. And there are some active sets. These are some connected components that needs to be extended. And originally this active set would be these guys. So active sets, these are like the active sets. It starts essentially with radius 0. And then you will go increase their radius essentially. So they have edges when you that only one of the endpoints inside. Because if both the endpoints are inside, then essentially it becomes one cluster. So you see, they are at the beginning they are like 0, and then do that until this point that these guys essentially collide. When they collide, and this is essentially the algorithm for Steiner Forest. This is the one that I mentioned, the Gomans-Williamson. This is the different interpretation of that. Like very similar essentially, but later there are some more changes. But with the coloring, so they have a different color, and then once the edge is fully colored, so this guys essentially is just doing the color of this edge. They are just color these edges. These are coloring. One edge fully colored. Then you will add this edge to your forest. And these guys, these active guys, they are growing. And so we stop and a set is not active if all the demands are satisfied inside. It means that like there should be no, for example, here it is not satisfied because this guy, the other part is outside, so it is not satisfied yet. The same thing here. So it means that they are still active and they remain essentially. One thing that becomes important is that, like, this is essentially this kind of some kind of sharing that they need to do that. Now these guys essentially collided into one, but now you want to extend it. The question is who should pay for it? If I want to go there, should I use the penalty of this guy? The penalty and budget are the same. Or the budget of this guy, which one I should pay? That's the problem that actually becomes more complicated for Steiner Forest, especially when we have the penalties, because before we didn't have these issues. I mean, Steiner Tree, everyone wants to connect to each other. So it doesn't matter from which one you are using. But here, these guys, I mean, they have a different penalty and they have different objective. And why I should pay essentially for connection of this guy, why I am not connected to this guy. That's the sort of problem that exists. So, but for a Steiner Forest, I mean, there is this problem arbitrarily they can pay. There is no problem for a Steiner Forest, but for price collecting a Steiner Forest then becomes non-trivial. And then here, for example, these guys are doing that, then, I mean, any of them, this guy or this guy can arbitrarily pace towards this until they collide with this guy. Now this guy is satisfied. So we bought this edge and this edge, and this guy is satisfied. This guy is not satisfied. So this still needs to essentially go a bit more. And then now these guys also collide and everything got satisfied. So far, again, there is no penalty here. So this coloring, all of them are growing at the same time and everything is good essentially. The only catch is the last one is that this is an important step. If you don't do that, actually, there is no guarantee for the solution. You need to remove redundant edges. So when you obtain here, we have this edge, this edge, this edge. But we don't need this edge. Because this guy is connected, this guy is connected. Why do we need this edge? This is the important step that you need to remove this edge. at the end. Then we get a two approximation for a Steiner Forest. What is the idea? Why do we get two approximation? This is the main idea, essentially, that you can get it from the coloring. So consider X is the total coloring that we are spending. The total coloring means total growing that we have done it. So I want to say that optimal solution is at least X. Why? Because of the intuition that I have mentioned. When you are increasing the radius, say there is a demand inside, and this is some ball around it. This guy, if you want to connect this guy to the outside world, you need to pay at least the radius of this guy. And that's the amount that we are using as a penalty, and this is X. But what, so this is about optimum. But what about us, or algorithm? Our algorithm can pay in average twice that. Why? Because if you have a ball here, there is this node here. Actually, you may pay the diameter of this ball in average. So if you have a ball here, the algorithm can guarantee that on average, so optimum just pays the radius because we want to bring this guy out. But our algorithm, you can say that on average is actually paying twice this radius or diameter of this guy. That's the reason that we get factor 2 for this problem. And that's the hardest problem that I have mentioned. So far, there is nothing better than 2 for Steiner Forest. Despite all the progress that happened for TSP, Steiner Tree, I don't know, all these problems, Steiner Forest 35 years at least, since even if not more than that, from the work of Agrawal, Klein, Ravi, we don't know anything better than 2. It's a very natural, and I mean, the mathy thing. As I mentioned, it started with Gauss for a Steiner Tree. He introduced it, but for a Steiner Forest, we don't have a solution. But this is the main intuition, and this is the only intuition that we have it, and it gives 2 approximation. And we don't know anything better than 2. Now, let's go to price collecting Steiner Forest and see what is the algorithm. So what was the price collecting Steiner Forest here? Each pair has a penalty. You don't want to connect a pair. So here, you don't want to connect a pair with a cost exceeding its penalty. Why? Because if you do that, why do you do that? Just pay the penalty for this guy. The issue is that, the one that I have mentioned before, you cannot do this kind of aesthetic coloring. Aesthetic coloring was the one that when you grow everything together, and then say, okay, you will maybe arbitrarily say that who should pay to buy. This case is that this is some kind of cost sharing issue. Why should I pay if I need to, at the end, I should pay the penalty? Why should I help the other guy to connect? And maybe, and actually not just this, the optimal may not do that. Decide I want to pay this guy, the other guy, if you can pay for your connection, then pay. Otherwise, it would be stupid to pay both the penalty of this guy and while this guy is not connected and just use some of this for that. So that's the thing that essentially makes this problem. This is the one that was the hard, essentially, issues about this price collecting Steiner Forest. It was not a trivial thing how you can do it. And when you have a different penalties, why, again, Steiner Forest, you have different pairs. Different pairs, they have their own penalties. They have their own budget. And you cannot just mix, essentially, these things. So this is actually this dynamic coloring. That was the thing that we have done it in with Kamal Jen in 2006. And so what is the dynamic coloring, essentially? So each pair, again, has a unique color. And then you will limit the colors of each pair by their penalty. Here, at any time, we have aesthetic coloring. However, this aesthetic coloring, in different rounds, it may change. So again, so in that sense, it is the case. So we are growing. But the catch is that the growing is not that smooth like the aesthetic case that all of them are grow together. So at any time that we want to grow a little bit, we need to actually solve the max flow things. What is the idea is that, like, I want to grow a little bit. The question is that from which penalty that I should use it. So this is the one that you need to decide, essentially. This is the graph that is called set pair graph that we create. And then we say that so far we have built this one. Now I want to epsilon grow all of them together. From which penalties should I do it such that I can grow epsilon? That's essentially the idea of this one. So this is essentially was a non-trivial thing. But using this, what do we do? Essentially, this is the algorithm. This was the algorithm with. This is the algorithm that I have mentioned. This was with camel chain. So you have some kinds of aesthetic coloring at each point. But if you want to essentially extend it, like if you want to grow this ball, you need to run this max flow things. And then if at some point you couldn't essentially extend some of these guys, you ran out of their penalty, you decide that these guys are dead guys, you need to pay their penalty. And you will repeat that. Those guys that are essentially paid their penalty, they are essentially satisfied in some sense. Then you can just continue with the rest. So we pay essentially, this is actually is important step is the minimal tight pairs. This is the one that we needed essentially this generalization of the paper that we had it with Kamal. So at any time, we try to keep the number of tight penalties minimal. It means that if you can get some penalty from one vertex and give it to another one such that both of them are not tight, do that. Good. So, and at some point, I mean, you need to run out of the penalty. These guys, they don't have any way to extend it and you need to pay the penalty. So this is the algorithm essentially. We consider this max flow thing with the minimum tight pair at any time. We pay the penalty for tight pairs. Whenever something becomes tight, we need to pay the penalty. For others, we are connecting essentially. And then at the end, we are removing the redundant edges. This is the same thing that was there with Commons-Williamson. And this one essentially gives a tree approximation for us. So we have our forest is at most twice the optimum solution. This is just, so someplace we bought something, this would be twice the optimum. And for some others, we paid the penalty. This would be essentially another factor that we need to pay. So this is two opt, this is another opt, and this is the tree approximation. And this was just essentially the little bit cleaner version of paper that we had it with Kamal Jen in 2006. But this was the tree approximation. You could do some trick, essentially get 2.54, but nothing better than that. Now, this was the algorithm. So this is actually, this is a very, now I can mention the algorithm. This algorithm was tree approximation. The people tried, even the integrality gap was above 2, so we couldn't do that. But there was a very natural greedy algorithm that if I wanted to implement this problem, maybe I have done that. What was that? I said, okay, you connect, essentially run this tree approximation algorithm. So if no penalty is paid, it means that we just connect everything. Then this is a solution to approximation. It's a very good thing. But if you paid some penalty, then what would be a natural algorithm? Get rid of these guys, those guys that you paid the penalty. Make their penalty 0, essentially. You know that you want to pay the penalty, so remove them. Run the algorithm for the rest of these guys. And then you will continue. And you will get several solutions, because each of them is a solution, correct? So you will just get this algorithm that you pay this penalty, and this is the tree that you have it. Then this guy you want to anyhow pay the penalty. So run the algorithm for the remaining pairs. See what is the solution there. Maybe more people you will pay the penalty. If you don't pay any more penalty, you are done. You don't iterate essentially. Otherwise, again, run it. You have several instances, take the minimum of this. Like very natural algorithm. And it turns out actually this algorithm is the true approximation for the problem. So, this is the algorithm that I have mentioned. Now, why essentially we get, this is the idea. So, if we are running this tree approximation, and if no penalties are paid, it means that we connected everything, and everything was happy essentially. This was actually the two approximate solution, because Steiner Forest, if there were no penalties, we could get two approximation. However, if we remove some of these demands, and then you will recurse, this is the one that we get to approximation for the recursive instance. This is the one that we are using an induction. And we can show inductively if this happens, then we get essentially two approximate solutions. And then we will return the best of them. Both cases, we get essentially two approximations. I will give you another view for this. This is another view. Actually, you can have it for these things. Especially, we have. This is actually very important things. So, these things that we are doing, this is essentially the idea. I mentioned that when we grow these balls, there are two cases that can happen. If the optimum essentially is this solution that we have it, and again, you can consider essentially when we are growing this ball, you can divide it into a small epsilon cases. If those cases that when you are growing a ball and we are coloring at least two edges of the optimum, these are good moments for us because optimum pays 2, we pay 2. And this will be satisfied at the end. So Gomez-Williamson can actually capture that. We don't need to do anything. The part is the part essentially that optimum pays 1, but we need to pay 2. And this is the part that this recursive algorithm is taking care of it. It makes sure that if optimum, and these are like all this, you need to, all this Maxwell business essentially to make sure that, but it just makes sure that when you, if optimum pays 1, we also pay 1 essentially, and we don't pay extra because of this recursive call. That's essentially the intuition for the whole thing. So I gave this intuition again, the same thing that I have mentioned. So if the single edge case essentially is the one that recursive can handle it. Multi-edge case essentially this Gomez-Williamson or AKR actually can handle that. And this finishes the proof. Again, there are some details, but that's somehow the intuition. And this is that's a thing that is, again, another thing. This was very natural greedy algorithm. We couldn't analyze it, but if you put together actually over, and the time that we designed this with Kamal, I mean, we were not sure that, this is the thing that we designed. We didn't know whether it can be used further. Interestingly, actually, a bit more better analysis of that algorithm with these recursive things, we could actually extend it and get this to approximation. That was, again, big open problem. Now, just briefly, I will say the same thing. Now, we could also improve this 1.79 approximation for price collecting Steiner Tree. This was the stock paper this year. And this was, again, we are using similar ideas. What was price collecting Steiner Tree? Again, you have essentially a tree, and you have a set of terminals. You want to connect them to the root. You can say that the root exists or not, because you can force always one node should be there, put the penalty of this guy infinity. Make sure that this guy is there, essentially. And this problem is NP hard. This is the example, for example. This one, if there are these are the penalties, you may connect these guys and pay the penalty of this guy. Now, this is our recursive algorithm here, very similar to the one that I have mentioned. There are some differences here. It is not trivial, essentially, to do that. You need to do some work, but this is the idea, essentially. So we run this Gomez-Williamson algorithm, the one that I mentioned, they had it in 91 or 92, essentially, for price collecting Steiner Tree. We run that, but with running with parameter beta, that beta is greater than 1, between 1 and 2, and the penalties are a little bit less essential. It means that they have less opportunity to grow. So we run this one, then we are paying the penalty for those guys that essentially they couldn't connect. For the rest of it, we are using a Steiner Tree on the rest of these vertices. And that is, as I mentioned, that is very good approximation. It is 1.39. If we paid some penalty here, we will do this recursion algorithm on the rest of the solution. And again, we take the best. Again, the intuition essentially comes from similar thing that I have mentioned. If optimum, there is a single edge case that the recursion can handle it. Multi-edge case is the one that essentially the original primal dual algorithm can handle it. And using this, but I mean, you need to have more details. You need to put some different weights, etc. And you need to do some kinds of essentially trade-off. And if you put this trade-off, essentially you get this approximation 1.79. Last slide, essentially, these are the open problems. Again, the main open problem, the major one is the Steiner Forest. Can we get anything better than 2? We don't know, any clue. The people tried, actually. And you cannot believe, actually, there were some stock Fox paper that the people tried to get. There are, as I mentioned, there are 2 approximations, but that's the only constant factor approximation that we know. The people tried getting 100 approximation or even 1,000 approximation. It seems, I mean, maybe not very wise to do that when we have 2 approximations. But the problem is so important, the stake is so high, that they believe that maybe if we get another constant factor approximation, later we can actually use it to break these 2. And these are the top conferences. Generally, that appear. It shows why this problem is so important. But anyhow, but for also for this price collecting problem, so this is the one that we have it. So for price collecting TSP, the best one is 1.59 versus 1.5 minus epsilon. For price collecting Steiner Tree is 1.79, 1.39. For price collecting Steiner Forest, at least so far we could get it tight result, but who knows? If we can get improved, someone can improve for Steiner Forest, then the question remains. Can we essentially trace it? And for price collecting Steiner network and submodular version, still we have 2.54 versus 2. So the main question, are there some hardness, real hardness between these 2? Can we prove that these 2 we cannot match essentially? Like there are some problems that you cannot get epsilon close to the solution. I mentioned there is this one for planar graph, but maybe it's not that satisfying. And essentially, yeah, can we close this gap, get almost this one, or there is a real gap that we cannot essentially break this barrier? And that's it.
Okay, thank you. So, any question?
Sure.
So what are the hardness factors known? I know you said there is nothing separating them, but for these problems,
I mean, for this one, generally we have just these are the hardness that we have come from the PCP. And for example, for the Steiner Tree, I think we have it. I don't know, maybe 1.10 or something. But you see, the same thing for the Steiner Tree or price collecting. No difference there. And still, these are much lower because
So
all come from PCP.
so they're very close to 1.
Exactly.
Okay.
And I mean, for the Steiner Forest is a huge gap. We don't know. Even non-price collecting, we don't know anything. I mean, yeah, it'd be very interesting to see any vertex cover hardness or something exists. We tried, so far we couldn't get anything for that.
And anything on directed graphs?
Directed graph Steiner tree essentially becomes arborescent. This is becomes the directed Steiner tree. For that, the best approximation is n to the epsilon. For any epsilon, and the main question is that can we get polylog there? That we don't.
Polylog. Okay.
So that I think in quasi-polynomial time, if I remember, you could get. I think maybe.
But there are some hardness results like 2 to the log something, right? For directed
for a Steiner Forest, there exists such result. For a Steiner Forest, is label cover hard essentially 2 to the square root of. But for a Steiner tree, directed Steiner tree, we don't know again.
I see. So even super constant is not known. Directed Steiner tree.
I think yes. There actually it is as hard as group Steiner tree. Group Steiner tree is log n to the 2 hard. So we know that for directed Steiner tree, we know something log n to the 2 minus epsilon and n to the epsilon. That's the gap that we have for directed Steiner tree. For directed Steiner Forest, this is essentially this is label cover hard.
Okay, thanks.
I have a question that you have talked about the price collecting clustering.
Yeah.
And I'm wondering if it can apply to the problems we talked after, like price collecting Steiner Forest or something. Can it improve?
I mean, not to price collecting Steiner. Actually, it can be. it has application. For planar graph, we could apply that. That was a JCN paper that I have mentioned. We could use that one as a procedure inside. So it's a very actually like a very useful tool. That whenever you want to have the connectivity, this gives you some ideas. The idea essentially says that you can create, if you have some confidence that this, how much this kind should grow, this algorithm gives you some idea that, okay, the optimum should not connect. This algorithm gives you some idea that which connected components you should do that. So you should not connect these, like you can say that the optimum does not connect these two guys, because if it wants to do that, it pays just too much. Because of that property that I mentioned. If optimum wants to connect from different clusters, actually pays more than the budget of this guy. That's a very useful thing that you can use it. Some of these papers, as I mentioned, you can take a look at it, and then you can just, it was very useful actually. Came out of price collecting Steiner Tree, but used for approximation of other problems, again, even some ML, some machine learning things as well.
Thanks.
Any question? So if there's no more question, let's thank Professor Hajiaghayi again.
Yeah.
So it's time for lunch.
Yeah. Thank you all as well.